Let me consider a parallelogram. Its opposite sides are equal and, of course, parallel. Each of them can be seen as the hypotenuse of a right-angled triangle of given cathetus. For instance, one side can be the hypotenuse of a triangle with cathetus A and C, while another side can be seen as the hypotenuse of another triangle with cathetus B and D. Since the symmetry of the figure, those triangles can be represented also on the opposite sides of the parallelogram. Well, I've been representing this figure in a way that can be included in a rectangle of sides A plus B, the bases, and C plus D, the height. Well, all of us know how to calculate the area of that rectangle. We will multiply A plus B times C plus D, basis times height, obtaining A times C plus A times D plus B times C plus B times D. Well, that gray area is made by different parts. We can also calculate the components of that area. We recognize two green right-angled triangles of sides A and C. Each of them has area 1/2 A times C, and in all the green area will be A times C. We have also two red right-angled triangles of sides B and D. Each of them has area 1/2 B times D, and globally the two of them will occupy an area B times D. There you see also two small rectangles. They are equal and they have sides B and C. Globally, they occupy an area twice B times C. And finally, the area of the big rectangle contains also the area of the parallelogram that I sketched now in yellow, and I call it D. Well, we have obtained a relation between different measures appearing in the figure, and we want to deduce from it the value of D. We can cross out some terms that appear on both sides, like A times C and B times D. And we cancel also once the product B times C. From that equality, we deduce the value for D, that is A times D minus B times C. We all recognize that this is the determinant of the square 2 by 2 matrix with first column A and C and second column B and D. Well, there is one more thing that I would like to stress out of this. Imagine our parallelogram represented inside a Cartesian plane. I will call U and V the two vectors coinciding with the sides of the parallelogram. Respectively, the vector U has component A and C, and the vector V has component B and D. Through our proof, we have showed that the determinant of the square matrix with columns U and V gives the area of the parallelogram with the sides U and V. Well, in order to write a correct formula, that determinant has to be evaluated in absolute value. Indeed, the area is a positive quantity. And remember that the calculation of the determinant changes sign if you twist two columns. And we want to obtain the same result if we calculate the area of the parallelogram with sides U and V and of the parallelogram with sides V and U.